All right. Good afternoon, everyone. And this is the second half of our chaotic journey. Hopefully, we get quantized very soon. But I still will uh, tell you a bit more about this standard map because I think we should train our neural nets a little bit about what's happening here. So let's just concentrate on this. Uh, let's just concentrate on this particular map. And okay, so to revise, this is a kicked rotor. So it's a free particle which is periodically kicked by this potential which is cosine. So it's like turning on and off a gravitational field of a rotor, of a pendulum. And this is the map. So this you should think of Q as the angle and P as the angular momentum. Okay. And this is just telling you that the rate of change of the angle is equal to the angular momentum. And this is rate of change of angular momentum. This is the impulsive force, which is given here. So this is an area preserving map. And we can also put a modulo 1 condition on the momentum and make this a map on the torus to itself. That is, there's a modulo 1 on both the Q and the P. So in that kind of a picture, we will look at this. There's a single real parameter K, which as we vary away from zero, it will undergo a transition from integrability to non-integrable. So it's a model, it's called a standard model because most of the pictures that we see, and you can see that it appears this transition is a generic kind of transition when you go away from an integrable 2 degree of freedom system. Okay, now first of all, let us note one rather simple thing. If the initial angle was zero and the initial angular momentum was also zero, that is q0 is zero and p0 is zero, then if we put this in the top equation, we get qn plus 1 is also zero. And pn plus 1 is also zero because this also vanishes. So that means that the 0, 0 is a fixed point of this dynamics. So that's a fixed point or a period 1 point of this dynamics for all values of k, irrespective of this k. And similarly, you can find rather easily one other fixed point, which is a fixed point for all k, namely when the angle is 1/2, q0 is 1/2, and p0 is 0. So 0 angular momentum, and this is 1/2. So 1/2 plus 0 is still 1/2, and 1/2 the sign vanishes, and so the 0 remains a 0. Okay. So there are two fixed points, and they will play an important role. And I told you how to find the stability of such a of such fixed points. You could do a linearization, find the Jacobian, find the eigenvalues of that. If the eigenvalues of that matrix, let me see if I have, yeah, I've written that down here. Find this Jacobian, and then evaluate this, and the Jacobian will be determinant 1 because of the condition of area preservation, and therefore the only quantity which really matters is the trace of this for the eigenvalues of this Jacobian. And so the trace condition is this. And you can see that for the fixed point at the origin, if you put 0, 0 here, it's simply 2 minus k. And the eigenvalues of this Jacobian matrix is 1/2 the trace plus or minus trace square minus 4 because the determinant is 1. And therefore, these eigenvalues will be complex conjugates of each other, and they will lie on the unit circle because the product has to be 1. So it will be e to the power of I theta and e to the minus I theta, and therefore stable, provided tau square is smaller than 4. So the condition for stability of such a matrix is that the trace should be modulus of the trace should be less than 2. Then such an orbit will be stable. So you can see from this that since this is the trace is just 2 minus k, that this is the condition for the fixed point at the origin to be stable. And therefore, if k is considered to be positive for us, we can also go negative, but let's take k to be positive, then it remains stable till k equal to 4. K greater than 4, it loses stability. And you can see that for the other fixed point that is 1/2 0, you will get a 2 plus k will be the trace. And therefore, for any k greater than 0, it is unstable. And therefore, there are these two fixed points. One of them is stable till k equal to 4. The other is unstable for any value of k greater than 0. All right. So, and the fixed point Lyapunov exponent, because it becomes unstable, there is a positive non-zero Lyapunov exponent for k greater than 4 is simply given by the log of the larger eigenvalue of this. And for very large values of k, since it's k plus 2, you can ignore the 2. You say that the Lyapunov exponent of the origin goes as logarithm of this k. Okay, and in fact, for k much larger than 5, the phase space is almost everywhere unstable. Almost every point is unstable. So there will be, as we discussed, a lot of periodic orbits and all that. Still, they will be unstable. And the Lyapunov exponents will be of these orbits is now calculated as log of k by 2. So you can see the slight difference between the Lyapunov exponent of the full system and the Lyapunov exponent of a single periodic orbit. But in any case, for large values of k, the standard map is considered to be chaotic with this Lyapunov exponent. Okay. In fact, if you look at the phase space as a cylinder, that is, you don't put periodic boundary conditions on the momentum, and you see what happens to the momentum as a function of time. If this parameter is much larger than 5 and the system is chaotic, it turns out that actually the dynamics of this momentum will look like it's a diffusive motion. It will look like a normal Brownian kind of diffusive motion. So the square of this momentum average over some bunch of initial conditions will be going as this linear power of time. And that's the diffusion constant given by this. So this is a deterministic system in which there is a diffusion, a normal diffusion going on at this. But there's a whole host of interesting diffusion phenomena in this deterministic map. Okay, so now let me show you a bit more of this dynamics as a function of k, but maybe I will show you interactively through this. Okay, so this is k is 0. I have put k is 0, and each time I click on this, that is the initial condition. And here, k is 0 is a constant, it's an integrable case. So this axis here is momentum. Let me just go down a bit. I don't know. Yeah, okay. So there are no numbers on this, but this is q. So think of the 0 to 1. This is momentum 0 to 1. Okay, actually in the program it's 0 to 2 pi, but that's just a matter of scaling. And this is momentum, so this is constant momentum at k equal to 0. And what happens when you click at one point is that it is iterating this 2000 times, and it's creating a bunch of points just along that line. So this is a quasi-periodic motion. You would call this a irrational torus. So that torus, which is there here in action angle variables, gets straightened out. So you should think about it as action remaining constant and this as the angle. Now, as we drag this, you see that there are some, even this blue trajectory, it looks dotted, dashed, not very ergodic. There's a difference between the green and blue. Why is that? So as I shift this, you can see that sometimes it's appearing as some dotted line. Exactly. So you are now close to a rational number in the momentum. These are actually, then you're close to rational tori. So this is what I said, that they're actually rational, irrational, intermixed in a very complex way, just as rational, irrational numbers are here actually exactly in that way. So half would be the largest kind of rational number, because I can't put it exactly there, but if it was there, you would see only 2 points actually speaking, if I can put it exactly at that point. Okay, I can't. So you're seeing that we're getting closer and closer to that. Um, so you have these irrational tori and rational tori. Now let us increase the perturbation. You're making it near integrable. We should expect from KAM that these irrational tori remain. This is what KAM theorem says, that these tori remain as tori, they just get deformed. Okay, they are otherwise remaining the same. But now what happens to these rational tori? So the most rational tori is this 0 by 1. Okay, and you can see that actually there's no tori there. Here you can see that already there is, this is not a tori, this is what is called a resonance. And in fact, I can put more points, I think. Yes. So these are all initial conditions. So you can now see clearly the unstable point at half 0. This is the 0, 0 stable point, as I said. Okay, and this is periodic boundary condition, so you should combine this with this point here. I mean, the up and lower line you join, and so you will see these rational tori, and now this is the fate of the one-half resonance. The one-half resonance does not follow the KAM theorem. None of these resonances do. And this is actually the content of Poincaré-Birkhoff theorem, which says that if you have a rational tori with, let's say, m by n is your rational number, this is actually the winding number, m by n, then n number of unstable points will be formed, n stable points will be formed, and these 2n fixed points will be actually interspersed. You'll have stable, unstable, and so on in a chain like this. So this is the simplest version of the Poincaré-Birkhoff. There are kind of other cases possible as well. So you can see here that the one-half torus breaks out into two unstable fixed points, two stable fixed points, this and this. And so yes, so these are the big resonances. So the smaller the denominator of the resonance is, the more rational it is in some sense, the larger will be the resonance, the nonlinear resonance region. And as you are increasing this, so you can see that there is now a thing which is rather close to a rational number, and so you have these. So this might be not a, this might be actually a chain of islands, very small islands, because I've clicked something close to that. So this is the near integrable regime. So as k is increased further, you can see what's happening to these. So the big resonance, the 0, 1 resonance is growing in size, and all of these resonances are growing in size. They are fattening up, and then there are these KAM tori which are fighting it out, and they are remaining. This k is now 0.76, it's quite large, and you can see that this unstable point here, the fixed point, remains unstable. This also remains stable, but around the unstable point, you start seeing these points here, so they are no longer curves, and in fact, chaos starts developing around here. It would also develop around these points here, which are also, yeah. Yeah, this is half 0. Q, yeah. Yeah, that is this one. Yeah. They are different. So this one is a stable fixed point. This one you can see is a stable fixed point, because I said that this loses stability only at k is 4. This is losing stability in k is greater than 0. Okay. So, and this you can figure out when you can work out quite easily what is the stability of the period 2 point. Period 2, by the way, is just momentum half, and q is 0 and half half. So at yeah, so you can figure out when that will lose stability. I think it's k equals 2. That is, you will have to now multiply the Jacobian here and see when its eigenvalues are not lying on the unit circle. Okay, so here it is still less than 2. This is now still stable, but now there is this unstable points here, and there's chaos forming also around here. And there will be unstable points here, chaos will be forming around here, and so on and so forth. So there are higher order resonances. And as this k is increased a little bit more, higher order, I just mean the number of islands. Okay, so this would be like a 0, 1 resonance. So there will be one island, and here there are 2 islands. There are 3 islands. Here there are 3 islands. This and this form one island. This is the 2/3 and 1/3. So you can see already all the rational numbers, big ones, 0/1, 1/3, half, 2/3. Okay, and you can see some tori which are formed here, which look like there are holes in it actually, and they may be. This is the mechanism by which this tori itself is losing stability. They form some kind of a Cantor set, fractal set as it's forming. Okay, so let's step it up, step forward. So this is now already gone to 1, and you can see, yes, so you can see more of that. This region is growing, and you can see more chaos in that. But at 1, actually, there is no, this one looks like a complete KAM torus, but actually, if you go for a very long time, some long time, this can penetrate this. So there are holes in this because there's a critical point of around 0.97 when all these tori are really breaking up. I don't know whether I want to try to do that. Maximum I can go is 5,000 steps, and in this program. Yeah, so when I click on this, you can see, yeah, you might need to go for longer in time before you can see that actually it is. And everywhere inside here, they just form stable islands. There are these stable islands here. Okay. So each time I click, you have an orbit that's formed in this. So this is a typical mixed phase space. You have regular orbits which are stable, Lyapunov exponent 0. You'll have unstable orbits with positive Lyapunov exponents, and they will be mixed in a rather intricate way. Okay, so let me step it up. Okay, 2. Let me look at 2. 2. Yeah. Orbits, yeah. Yeah. So I have now clicked so many times that there are many things. I can remove each of them like that. Okay, but I've clicked too many times, I think. There must be a way of removing everything. Oh, hide. Okay, no. There should be a way of clicking. I can go till 2000. It doesn't. So each time I click on this, so let me probably, if I want to, doing the dumb thing. Each time I click, so I can create more initial conditions if I want. So right now there is only 2 initial conditions. Okay, so let's remain with 2 initial conditions. So here is a case of 1.14 and just 2 initial conditions. I can even make it 1 initial condition by removing that. Okay, so this is which one? So this is now only 1 initial condition. Okay, this is at k is 1.52. So you can now see all these. So now this is a single orbit. All of these are single orbits. Okay, so you're seeing a variety of them depending on where you start. It can be chaotic. It can be some. So you can see this orbit, for example, it's accumulating around these points which are clearly where there is a stable point. I can go for longer here. Okay. So now let's go to 2. So 2 is actually a case where this point still remains stable. This fixed point still remains stable. But this fixed point at this period 2 orbit actually becomes unstable. You don't see that. You see as if there's an island, but it has lost its stability through a bifurcation. And larger than 2, you will see that it disappears rather quick. Well, 3, it has disappeared completely. So the period 2 island has disappeared. The period 1 fixed point here, which is stable, remains stable. As we know, that gets destroyed only at 4. So let's go at 4. 4, this has become unstable. You don't see that exactly that point will remain unstable through a bifurcation, and but surrounding it, there are stable orbits. So you're seeing the island still, but quickly after that, that also disappears, and now it's rotating something. Yeah. So this is 7 and so on. Yeah. So 4, this has become unstable. You can see these structures here. Okay. So this is an island formed here. So this has lost its stability. If there is a single orbit, it will just cover this whole thing ergodically. But there are still these islands fighting it out for, they can remain stable. And as you go by, that also disappears. So here it looks like there are no stable parts of this thing. Every single point will go arbitrarily close to every other point. This would be a completely mixing system. But you never know, there could be small islands which come on the way. For example, this 9.28, you can see that there are these small islands which form. Okay, so that's how the standard map phase space is. So any questions about that? So let's move on. Yeah, so these are the, yeah. No, it's not monotonic with K. Largely it's monotonic, but you can't say that simply it's monotonic. Here, that's why I'm showing you an example of 9.26 versus 9. Huh? Yeah, well, these are having to do with how these islands are formed. That's due to some what are called tangent bifurcations. I'll show you a little bit about stable, unstable manifolds of even fixed points. They typically transversely intersect. If they don't, then they form islands. So it's actually a very complicated situation. Like even this simple map, there are several things known rigorously mathematically, but given any value of no value of k, you can say with certainty that there are no islands. K equal to 9, it looks like there are no islands, but it's impossible to show that so far. Unlike, for example, billiards, several of the billiards which I showed, I told you it's completely chaotic, or many other maps. But this is a smooth map, which it's difficult to actually show this analytically. Okay, but yeah, these bifurcations are pretty well understood. I must say that two-dimensional area preserving maps are the best understood, not even 4 and so on. Okay, so 2 is rather well understood. Okay, here is a doubling map, which doubling map we saw as a simple solvable model. So that there is an extension of this to two-dimensional area preserving map, which is also solvable in exactly the same way. So remember that the doubling map was this 2qn modulo 1. So here now you have q and p, and it's 2q modulo 1 in the position still, but in the momentum you divide by 2, so that it's area preserving. So 2q p by 2. And for it to be area preserving, if q is greater than 1/2, you divide by 2 and you shift by 1/2. So this is a mapping of a square into itself, and the dynamics is again most simply a left shift. It's a complete double-sided left shift if you express these initial positions and momenta now in binary. So you express this in binary. Q0 is A0, A1, A2, etc. And then the initial momentum you put on the left side of this. So A minus 1, A minus 2, A minus 3. So the initial momentum is like this. So now you can see from this easily that the left shift is the same as before in Q. So this A0 is going to, the most significant bit of A0 is going to be lost, but actually here is not going to be lost. It's going to go into the most significant bit of the momentum. So this is why it's now a reversible map. There it was not a reversible map. Now it's reversible. It goes into A0 here. Okay, and so now you can see what's happening. The whole thing is a left shift like this. There's no loss of information in the Baker's map. It's completely chaotic. Its Lyapunov exponent is log 2, topological entropy is log 2. There's a uniform invariant measure, and it has been shown rigorously that it's isomorphic to a Bernoulli process. Therefore, you can say safely that this is a deterministic system whose stochastic properties are as random as a coin toss, rigorously. If you have a one-to-one, you have a coin which you're tossing, a fair coin, you get a sequence of heads and tails, you can map any sequence, random sequence, to an orbit. There's a one-to-one correspondence between an orbit and a random sequence of coins. So what happens here is, so that to see this, you take the square, you cut it vertically into two halves. The red half, you just squish it down by a factor of 2, and you elongate it by a factor of 2 along the position so that it comes to this bottom half. And similarly, the blue half, you squish it vertically, expand it horizontally, and then you stack it on top. Okay, so this is the process, and you can see very quickly how it is mixing. Yeah, it does that, and then it continues to do this in the stacking way, and then it just completely mixes. Okay, so that's a solvable model. Again, completely all the periodic orbits you can find. There are 2 power L periodic orbits. You can find out where they are. I leave it as an exercise. All the orbits can be found, not just periodic orbits. All the interesting orbits can be found here. You can find that it's a dense set, and so on and so forth. Almost all the arguments for the doubling map go through. Okay, so here is another very well-known map called the Arnold-Cat map, studied in the same book where I showed that mixing, Arnold and Aves, ergodic problems of classical mechanics. And this map looks linear, ABCD. ABCD are constants, except that it's now on a torus. So there is a modulo 1 condition, and therefore this ABCD have to be integers. And if they are determinant 1, it's area preserving. Okay, like for instance, the Arnold-Cat itself is sometimes just 1, 1, 1, 2. So clearly area preserving, 2 minus 1 is 1, and they are all integers. And it's called a cat map because Arnold and Aves put a picture of a cat in it and showed what happens to the cat. It's almost like the Baker's map, except that there were these 2 binary symbols. Here there are 3, and it's a subshift, it's not a full shift. But you can again show many of these things that is isomorphic to a finite Markov process. So it's stochastically like a Markov process. Okay, so there are various things that you can put. I decided to put Rajnikant here because the cat map is also very special. So let's see what happens to this image under this iteration. So you take this image, it's a 256 by 256 pixels integer array, and then you are applying this map to this, okay, to this integer array of this. So it's actually a permutation of the integer array to itself, and this is what happens after 1 iteration. So it's being pulled and stacked. So you can't see Rajnikant here, but actually you can go reverse. This map is invertible, remember? So you can actually go reverse. So this is after 2 iterations, 3, 4, 5. So this has all the information in this. You can run the machine backward. So this is kind of used in cryptography and so on. But this is what chaos does. It mixes in this. Huh? Sorry? It is permuting the pixels. If you wish, there are 256 by 256 pixels. What it is doing is it is rearranging these pixels in this manner. And actually, if you wait long enough, you can see these patterns are developing. This is completely dynamics. Very interesting. It depends now on how large a size your grid is, 256 by 256, 1024 by 1024, etc. You can see that Rajnikant being superstar survives this process, but it will take him 196 iterations and would come back. So this is an example of a Poincare recurrence, a long time recurrence, but it's exact and it's very specific to this cat map. It will not happen if you put this on the Baker's map or on the standard map. There's a nice paper by Dyson. Yeah, so he came back around 196. Huh? Very good, exactly. M to the power of 196 is not identity, modulo 1. Modulo is the most important because M has eigenvalues which are larger than 1, it's chaotic, it's stretching. So uh, M to the power of N is the dynamic, so it's again completely solvable, but it's modulo 1. So this modulo 1 is creating so all of these things, and you can actually check this easily. You just take 1, 1, 1, 2, keep multiplying, you'll see Fibonacci numbers. So it's some number theoretic properties of Fibonacci numbers which will give you this periodicity. Okay, so and you can show that this is mixing rigorously in the following way. Okay, what is mixing? So I showed a kind of thing about the one-dimensional maps where you were going to the invariant density in time. Here, the invariant density, by the way, in all area-preserving maps, the invariant density is just a uniform measure on the phase space, on the torus or whatever. Uniform measure meaning just the area, Lebesgue measure. So it's uniform on this. It remains uniform for any of these maps. Any Hamiltonian system, it is the microcanonical ensemble. The microcanonical ensemble where is the invariant density. If you take some non-equilibrium density, is it being pushed to the microcanonical ensemble? This is, of course, a thermalization question. And in these cases, you can show in what sense is it thermalizing. If you take a density here at time 0, okay, this is Liouville's theorem. It says that the density at Qn at time n is the density at Qp at time 0, where this Qn and Pn are related to Qp by an inverse map. So you get Qn Pn is got by iterating Qnp to a time n. So to find Qnp, you need to go back in time for Qp by a step n. So this is solving Liouville equation. So we set the Perron-Frobenius equation. Here, it's a one-to-one map. There is no, so it's even more simpler. There are no other branches to this. And now we have to solve this. So to solve this and see what happens when n goes to infinity, again, because it's a torus, it's important. It's completely suggestive that you should do a Fourier transform with some coefficients. You expand the initial density like this, and for this to be integrable, the zero mode is 1, and then you can show for the cat map that this can be written like this. After a time n, the density is given like this, where these vectors, these k vectors or the momentum vectors or the Fourier space vectors, they are being multiplied by this m to the power of minus n. M is this matrix whose powers are growing exponentially in time with a Lyapunov exponent. So these are exponentially growing. So this means that you can actually shift it like this. What it means is that the modes which survive, actually the power in the modes are increasingly going into the higher frequency modes. And this is except for the zero mode. So the zero mode survives as it is, and the others get highly, very large, exponentially large wave number oscillations. So the density will never strictly become uniform, but for all practical purposes, if you take a test function, it will be uniform because it's got this uniform measure. It's never going to just 1, but it's got this exponentially large wave number oscillation. So this is the price you pay for reversibility. So thermalization occurs in this sense in Hamiltonian systems. In fact, in these pictures you can see that these are highly, the wave numbers of this are growing. You can see that it's finer and finer structure from this. Okay, so yeah, so mixing, I've already described that. So you can go from this. What does mixing imply for correlation functions? So if you take any function on a phase space, phi 1 and phi 2, let's say, are two functions on phase space. You evolve one of these functions. So x is phase space. It can be any number of degrees of freedom. And this mu is the invariant measure. So that's a correlation function approaches the uncorrelated integrals exponentially in time. If it is exponentially in time, it's said to be mixing. And these numbers are called the Polycott-Ruel resonances. So those are the mixing rates. They are rather hard to find except in some simple systems such as this.
So what is happening? You are like phi 1 infin x, phi 2x dx, minus phi 1 x. So fn x is like the dynamics.
Yeah, fn is the dynamics. Yeah, fn is the dynamics. N is the time.
And you are doing it with respect to this invariant.
That's important that it be with respect to the invariant measure. If you don't do that, then yeah, you will have to be, because if you integrate just this, any function here, fn x, d mu x, that is equal to the function d mu x only if this is an invariant measure. You can transfer this fn x to the measure, and you can do that. Yeah, they tell you how fast the mixing is happening in phase space. Yeah, they are like in the case where in the 1D map there were these Perron-Frobenius operator. So they are eigenvalues of that. In this case also you can write a Perron-Frobenius operator and look at these eigenvalues, but it's quite an involved exercise because it will be unitary matrix strictly. It's a bit like these resonances which you were talking about in scattering kind of system. So you have to expand your functional spaces, and then you will find these eigenvalues. You will find these eigenvalues. It's it's not that, but any correlation function you take and it decays exponentially, those are actually the resonances. Okay, so yes. So finally, there is an ergodic hierarchy classically. We have looked at ergodic systems where phase space average in some sense is equal to there is an invariant measure, and the phase space average with respect to that invariant measure is typically time averages. But here every orbit comes arbitrarily close to every other point, but there need not be mixing. Okay, like for example, the irrational rotation is ergodic. Mixing is the higher level, so mixing implies ergodic but not the other way around. Kolmogorov is actually where these correlation functions are decaying exponentially. Correlation functions can decay algebraically, it will be still called mixing, but if it is decaying exponentially, it's called Kolmogorov. So example like the cat map is a K system. Bernoulli is when there's no memory at all, it's like a Bernoulli process. So the Baker's map is an example, and I believe some of the billiards are also proven to be Bernoulli systems. So this is an ergodic hierarchy. Bernoulli are Kolmogorov, Kolmogorov are mixing, mixing are ergodic. Okay, so that's a summary of classical ideas. Chaos implies this, ergodicity, dense set of unstable orbits, sensitive dependence on initial conditions, typically exponentially. For an n-dimensional phase space, there are 2n Lyapunov exponents, which comes from this large Jacobian matrix, the Lyapunov exponent spectrum. The Hamiltonian dynamics, n degrees of freedom, 2n Lyapunov exponents, they come in pairs of plus minus, so that the sum of the Lyapunov exponents is 0. It's a consequence of volume preserving flow. Topological entropy is the growth rate of the number of periodic orbits and is greater than or equal to the Lyapunov exponent. I did not talk about the Kolmogorov-Sinai entropy. It's the rate at which a phase space gets partitioned. You take an initial partition and you see how fast it's partitioning further. It comes up in a lot of physics. For fully chaotic systems, we can just think about it as a sum of positive Lyapunov exponents. So that's sufficient for us for the moment. Almost all low-dimensional systems have a mixed phase space. There is both regular and chaotic orbits. It's expected that as the number of degrees of freedom grows, it typically gets chaotic. The number of regular orbits goes to 0, but this is not rigorously shown. There is a lot of results, but that's kind of expected at this point. Mixing occurs at different rates. Now, this mixing is different from this mixed phase space. This is the mixing that I just talked about for correlation functions. Okay. All right. So that is, yeah.
The topological entropy, which you said growth rate of periodic orbits, I guess.
Yeah.
Unstable periodic orbits.
Yeah. Yeah.
So that versus this Kolmogorov-Sinai entropy, which you are saying somehow positive Lyapunov exponent in simple sense, are they showing similar behavior or would they show different behavior?
Yeah. Again, topological entropy will be larger than the KS entropy, but they are all in the ballpark. They're all kind of similar because conceptually they're all quite different. Kolmogorov-Sinai entropy is kind of telling you how much information is being created. In a chaotic dynamics, information is created, unlike in a regular dynamics. Because as you're seeing a trajectory evolving, you may try to measure the trajectory and try to see where it's coming from. Like for instance, okay, this is like take this table and you have a particle moving in this. Okay, let's partition this table into two, left half and right half. Now somebody just keeps telling us left, right. What happens? Is it in the left, right at given times? So if the dynamics is chaotic, this information that you're getting will be valuable. You're getting more and more information about the initial condition in this process than if it is regular. For example, in the absolutely trivial case, let's say that it's always on the left for some reason. Then you won't know anything. You will just get left. Yeah, but so you won't get any information. There can be many periodic orbits with the same thing. You won't zoom down to a periodic orbit. So Kolmogorov entropy is kind of it measures it measures the, so you see Lyapunov exponent is very different. It's telling you the rate at which things are going diverging, whereas the Kolmogorov entropy is more related to information theory and thermodynamic entropy. So you can see that it is more related to thermodynamic entropy. Lyapunov exponent is not an entropy at all. Lyapunov exponent is anyway not an entropy.
So, but you said it's somewhat positive Lyapunov.
Yeah. Right. For a fully chaotic system, this turns out to be the case.
But then, if a chaotic system is Kolmogorov-Sinai entropy will be similar to Boltzmann entropy, or that also does.
People have looked at some systems where it has been shown to be like the thermodynamic entropy. So you can make connections to that. Yeah. There's no regular region. Actually, it is even more than that. Hyperbolic in the sense that every part of phase space is stretching and expanding. Every part of phase space is stretching and expanding. The standard map, for example, is not like that. Even for large K, every part of phase space, you will not find that there's stretching and expanding. The Jacobian eigenvalues will not be all real anywhere in phase space. So those are called hyperbolic systems. So strictly speaking, hyperbolic systems, this is a theorem called Pessin's theorem, P-E-S-S-I-N, Pessin's theorem. Yeah. Okay, so let us go to finally the promised part of the promised land of quantum. So let us start simply with with the standard map. And what I'm going to do, it's still classical, okay? So I've taken a bunch of initial conditions.
Is it the kicked,
It's the standard map, the kicked rotor. Okay, I've taken a bunch of initial conditions at the center, half half, and I'm seeing what happens to it with time. Okay, it's just free particles because k is zero, is integrable, and k is, I mean, half half is a period 2 orbit. That's why it went here and there, and then it did this. Then it's spreading along this. Okay, so it just spreads along this pretty much uniformly. That's what classically is doing. You can see initially the period 2, but then it's expanding along this, and then there are these orbits near the period 2 that it's getting stuck at. It's just getting sheared. This is what happens to free particles. It gets sheared. Now, let's see what happens to k is 9 when it's fully chaotic, the same initial things. So you can see that it's now all over the place, this bunch of initial conditions. So that's kind of, individual trajectories are unpredictable. However, there is simple statistical behavior. A very short time, things just get uniform, let's say. Okay. So ergodicity, I've already said. Mixing, I've said what it goes. But this is evolution of densities. Now, quantum chaos, 1979, is perhaps the earliest papers. The Tabor-Berry earlier than that is really an integrability paper about integrable systems. So anyway, so there is no phase space at all. Our favorite object that we have been looking at so far is unfortunately not there. We have some mysterious Hilbert space instead. There's no phase space because the position and momentum, canonical position and momentum don't commute, so you can't specify position and momentum. That's what they say. And there's I h bar. And therefore, there is some coarse graining happening at a h bar scale. There is a coarse graining happening. How does classical chaos impact quantum spectra and time evolution? For a long time, this has been the question. There is a 13th century poem, Eat No Fish But Red Herring Red. Clearly, spell check is not there at that time. So this is a definition of a red herring. Red herring is a fish from the practice of drawing a red herring across a trail to confuse hunting dogs, something that distracts attention from the real issue. So there are many such things around quantum chaos. One is that there is no quantum chaos because quantum evolution is unitary. So if you take a initial state, and that's the time evolution e to the minus iht with any Hamiltonian, integrable, non-integrable, whatever it is, and you have the state at time t. So if you take some other state, psi1 and psi2, which are very close by in some sense, it doesn't matter. However close by they are, the inner product, which measures kind of the distance between them, is not changing at all. There's no sensitive dependence on initial condition. But I can argue also that classical evolution is also unitary. Phase space densities, like what I showed you just now, they also evolve unitarily. They evolve by exponentiating the Liouville operator, where the Liouville function, you see this is the Liouville operator acting on a function, is just it's a Poisson bracket of the Hamiltonian with f. This is classical. If you put an I there, this object will become Hermitian. And the evolution is linear. Densities evolve linearly in time. And in fact, entire classical mechanics can be put as an evolution of densities. Any given phase space point, density is a delta function at that point. Quantum evolution is linear, and therefore the Schrodinger equation, we know it's a linear in time equation, and therefore it cannot be, chaos is because of nonlinearity, and therefore there cannot be quantum chaos. But classical mechanics can also be cast as a linear theory completely. It has been known for a long time. Again, it's basically like a Liouville equation. The Liouville equation is linear, and this is for the densities. Okay, this is the it looks exactly like the Schrodinger equation. Well, it looks more like the Heisenberg equation. So the Liouville equation is can give you Hamilton's equations. It's equivalent to the Hamilton's equation. Nothing wrong with this. For instance, if you put q there, that will give you dq by dt is p. Okay. So in fact, the Hilbert space formulation of classical mechanics has been known for a long time, since 1931 actually. Koopman he showed that classical mechanics can be formulated on Hilbert space, it's unitary, and so on and so forth. In fact, von Neumann used this to prove what is called the ergodic theorem. Birkhoff did a more general proof of that. So all of these things about it being unitary and linear are all red herrings. That's quantum chaos is something more deeper than that, and there are many applications and examples for a long time. Just a very short list. Right at the beginning of this, there were these heavy nuclei in which there are resonances, QCD. All of them are describable kind of by what I call random matrix theory, and there's supposed to be quantum chaos in these things. And some of the most early experiments have to do with atomic physics. They have to do with hydrogen atoms excited, like Rydberg atoms in strong microwave fields. So you already have a Rydberg atom; it's highly excited, principal quantum number, and then you kick it a little bit with electric fields. That is sufficient for you to create chaos. Also, you could have hydrogen atoms in strong magnetic fields, so that you're going beyond the Zeeman effect. In fact, around 5 Tesla or so, that's sufficient for you to drive the system into semi-classical chaos. What happens? A hydrogen atom, Kepler problem. So you have all the constants of motion, you have integrability at the level of treating it a non-relativistic quantum mechanics. But you can break that by breaking the symmetry. For example, with a magnetic field, it becomes cylindrical symmetry rather than a rotational, fully spherical symmetry. That's sufficient for you to introduce chaos at different energies. So atomic physics, even the simplest atom, hydrogen atom in external fields, you have to deal with all these issues. Helium is already born a 3-body problem. So beyond perturbation theory, you need to go into a 3-body problem, which is the central problem of the earliest problem Poincaré considered of chaos. So the whole of that, molecules, it's a whole lot of quantum chemistry are examples of this. Mesoscopic transport in quantum dots as quantum dots, and manipulating single electron motion in quantum dots became possible. There was ballistic quantum billiards. We saw these billiards, so people could shape billiards according to a stadium billiard, circular billiard, etc., and see the differences in the transport and so on. Phase transitions, spin systems, quantum computers. So now quantum computers are in the air, and they are basically interacting many-body system. Josephson junction. By the way, what is a Josephson junction basically at the end of the day? Pendulum, in fact, right? It's exactly the pendulum, and the fact that you have many of these together is coupled pendula. You're asking for it, and that's precisely what happened. What happens? You will see that there is, even without any computation, putting together all of these junctions together is very much a playground for quantum chaos. So you have to watch out when you're trying to do controlled operations on a quantum computer. By the way, not related to chaos in the computer, but the proofs of so-called quantum supremacy of a quantum computer essentially relies on quantum chaos kind of arguments. Hopefully I'll have time to do that. And recently there's a lot of interest in quantum metrology. It looks like quantum chaos can be really useful in measurements, in aiding measurements. So this looks kind of anti doesn't look very reasonable, but chaos has a lot of ingredients to make for a good measuring device. So you might have practical applications there as well. Foundations of quantum statistical mechanics, quantum field theories, quantum gravity. There's a lot of work now surrounding these things. Just very rough. Okay, so what I want to do is I've introduced these simple models. Now I want to study the quantum mechanics of these simple models because we have hopefully trained our neural nets a bit about chaos. So we can, when we go to quantum, we can see the similarities and the differences. So for example, the standard map. We want to look at quantum standard map. So we looked at kick systems such as this. Okay, so let's look at the quantum mechanics of kick systems such as this. So we have a Hamiltonian, which is the sum of two parts. One is head zero, can be anything, plus a potential, can be, need not call it potential, but let's call V, it's time independent. All the time dependence is in this series of delta kicks, okay? So it's exactly that Floquet system that we are looking at, and this is Schrodinger's equation for a time evolving state psi, which we would like to solve. Now, the map, remember we derived a map for this, which related the state Q and P just after two consecutive kicks. So we will define a quantum map also in the same way. If the state just after kick n is given by this psi n plus just after kick n, find the operator u such that u acting on the state gives you the state after the kick n plus 1, just after the kick n plus 1, okay? And from general quantum mechanics, we know that this operator is unitary. So this will be the equivalent of the classical map. And we'll call this quantum map, although in quantum information literature, a quantum map is also used in other ways. So between n and n plus 1 kick, you see, we'll follow exactly what we did for the classical. In the free part, it's very simple. So between n and n plus 1, the kick n and n plus 1, this is not operative. So it's just e to the power of minus I head 0 t by h bar. There is a time t, that's the time between the kicks. And this is the state just before the n plus 1th kick. Okay. So now the most important thing, as we did there, is to integrate across the kick n plus 1. So I'll argue in the most simple way, almost like that head 0 is ineffective at this. Otherwise, you can integrate over a short time or a infinitesimal time and throw this away. So let's say that head 0 is ineffective, or we just ignore it. And this equation is now of this general form, I h bar d by dt, the rate of time, v times g of t. I've just introduced some time function rather than this plane of delta function. But you can solve this easily because these are actually commuting operators. We study in quantum mechanics 101 that this is basically the integral. Okay, so this is now psi of t prime. This is the state at time t. And you have to integrate this g from time t to t prime where you evaluate. So now here, this g of t is this train of delta functions, and we are going to evaluate this at n plus 1th delta function. But integrating a delta function simply gives you 1. Here there's a divided by t, so it will give you a factor of t. So this is simply giving you this e to the minus I v times t. Instead of head 0, this is v times t, and this is the state just before the n plus 1th kick. But just before the n plus 1th kick, it's given by this, so we'll put in the exponential part and this thing. So now we are complete. This is the state after the nth kick. This is the state after the n plus 1th kick. This must be the unitary map which we are looking for. So that is why this is very simple. So the quantum map for the Floquet kicks are very easily derivable. It is just a product of these exponentials. If there was a sum, it will be the exponential of the sum. That would be, for example, just head 0 plus v. Here it is a difference between that and the product. But you know that the exponential of non-commuting operators is not the exponential of the sum, and therefore this is not the same as the other one. So in particular, if this H0 is kinetic energy like P square by 2 and this V is V of Q, the classical map is given like this, and this is the quantum map. So it connects the states, so this connects the states just after kicks, just before kicks, first the kick and then the free motion. So it's just interchanging this order. You can also derive a map which is connecting halfway between kicks. So then you are deriving halfway this free motion, then the kick, and then halfway the free motion. All of them are equivalent. It's only how you're defining the base time. Yeah.
So you see that there are two maps for classical Q and P. In the classical one, when you are writing Q n plus 1 and P n plus 1 separate writing, right? Here with U. If you go back to density that Liouville equation, would you be able to write only one equation for
the classical, you mean? Yeah. The classical, the Liouvillean, or the Perron-Frobenius or Koopman, whatever operator, it's a single operator. Yeah. Because it's acting on functions of phase space.
So the Liouville map will be
one operator, exactly. The Liouvillean operator will be one operator. Okay.
So what is the difference between Liouvillean operator versus U?
Similar, yeah. So that's what is interesting to study these things, right? But here you have a H bar. There's no H bar. There are these. So in fact, the Liouvillean operator typically in classical mechanics much more complex object. You'll have continuous spectrum, all kinds of spectra. It's very little is actually known about the classical part. Quantum is easier in some sense, but it is also conceptually different. It's conceptually different. There are
easier, but if you take down large number space, would it match?
H bar tending towards 0. It should match with. Well, whether it should match with Liouvillean is not obvious because the Liouvillean is acting on densities. Okay, so U is acting on these pure states. So there is some equivalent. You should look at the proper object and then it will you can proper quantum object because this is acting on states.
So instead of state machine, it should be something sign
It should act on density operators. It should act on density operators on one way. So it's like a Heisenberg thing. So this is a conjugation. You should do a direct action. So U, I would say that the unitary operator U itself in quantum mechanics does not have a proper classical limit. It has semi-classical limits, very important. And that's also kind of natural from, you can see H bar is appearing in the denominator. So as H bar tending towards 0, its limit is singular. So it's not a good object to deal with quantum classical correspondence. Okay, so the most important thing is it's coming from a product of non-commuting operators, and therefore these might be simple spectra itself, but this product can contain in it all the quantum chaos that we want. Okay, now on the cylinder, let's look for the standard map on the cylinder. Okay, so this is a free particle, so kinetic energy or angular momentum term here, and this is the potential term here. This is G is the kicking strength, T is the time between the kicks, there is a H bar. So this is the operator that we need to deal with in the quantum standard map. Now let us write this in the topology of a cylinder first. Okay, so Q has got periodic boundary conditions, so you should think of Q as theta, but I'm considering there is V is this form, cos Q, cos 2 pi Q. H0 is P squared by 2. Okay, so we can take periodic boundary conditions in the position angle, let's say, then that will imply that the angular momentum is quantized. Okay, it's always the conjugate that will get quantized. So you can see that quite simply. We require that the inner product of q plus 1 with p is same as q with p. But now this qp always has this inner product which is a Fourier transform e to the I qp by h bar. So now you put q to q plus 1 and require that that be equal to qp. You will get that p is a multiple of 2 pi h bar, integer multiple of 2 pi h bar. Okay, so this is just the standard angular momentum being quantized. Okay, so nothing more deeper than that. So you have an angular momentum is quantized, and this is the angular momentum equation, and the angular momentum value, integers can take values like this. And this inner product is between q and an integer m is given by this Fourier transform. You can write the momentum vectors in terms of position. So now we can take this object, this operator, and express it in momentum representation. This is convenient because that momentum are integers at least. So we can have a matrix which is which has some discrete indices in it rather than an integral operator. So we can write a matrix umn. So we'll take this operator, sandwich it between momentum states m and m prime. Now this is simple because it is already an eigenstate of p square. So that just leads to this quadratic term here, t m prime square. And then you have to calculate this. So we do the standard trick of inserting this position thing, and you have an integral over that. So you have an integral of e to the cos theta with this exponential terms. But that's the definition of a Bessel function. So the matrix elements of the quantum standard map on the cylinder is given explicitly by this expression. So this is coming from the kinetic energy, m prime square, and this is coming from the potential energy. It's a Bessel function m prime minus n order, and the argument is k, which is the kicking strength. Now this is the classical kicking strength parameter divided by tau h bar. What is tau? Yeah, so now these are the effective, this is the classical, and tau is related to the time between the kicks. Now here is the first difference which you see between classical map and quantum. Classical map had only one effective parameter, capital K. Now there are two parameters, they form either K or tau h bar. K and tau h bar, or K and tau if you're fixing h bar. Okay, so there are two parameters to play around with in the quantum standard map. There's increased complexity in this object. So this was actually the first, I would say, important quantization done in the late 1970s, and the early experiments were done on this, both numerically as well as experimentally. So we have an initial state, it could be a momentum state, yeah. Yeah, it's not expected, it's more like an inner product. Yeah. Why this? Because you want q plus 1 to be q itself. You can have phases, but let's say that you have a periodic angle. So here, like, an angle by, if you shift by 2 pi, it's the same as the original angle. It's the same thing here, just my angle, the 2 pi is 1 for me, that's all. So the state q itself is equal to the state q plus 1. And therefore the inner products are the same. Okay, good. So let's say that we take an initial momentum state 0. Okay, so 0 angular momentum, we act on it with this quantum map t times. So t times we are kicking the thing, and we are asking for the state psi of t. This is simply given by this. But this matrix is infinite dimensional. So you need to, if you are doing any numerics, you have to truncate this and approximate it. Okay, the full infinite dimension is unitary. Truncation need not be unitary. So let's calculate, for example, the expectation value of momentum, okay, as a function of time. So then you need to calculate the expectation value of the p square operator in the state. And you can express this in terms of this m, which is the momentum. Then this is what you need to calculate. And as I already said, for the classical, if you calculate the expectation value of momentum square with time on the cylinder, for large k, it undergoes diffusive motion. It's like a normal diffusion with this diffusion constant. So you can ask whether this holds for the quantum case. So in fact, to kind of demonstrate for you that it looks diffusive, I have just done this simulation, momentum versus time, and starting from zero momentum at zero time, but with different angles, different q. Okay, and you can see these kind of momentum things over 1,000 times. You can see the momentum is oscillating between some 20 and minus 20. You can kind of see already the square root of t, t in the momentum thing. So that momentum square is going as time. It's looking like random walks. Huh? No, I'm not even doing anything here. I'm just plotting momentum for given initial condition. Classical. This is purely classical. So the average of these will give you this. You take the square of this and average, it will give you this. So that will give you this nice straight line. Okay, so this is classical line as a function of time t. This goes linearly in time, and this is quantum. This is the parameter is k is 5. So remember that k is 5 is pretty chaotic, and tau is 0.25. There are actually two parameters here. This tau is an effective, h bar is 1. So tau is tau h bar is 0.25. So no, it's around that. Okay, so it's not very small. So this is quantum. So these are my own simulations. So it's not that great at this point, but this has been worked on for a long time. But what this shows is that the quantum diffusion is much smaller than the classical diffusion. And in fact, for a very long time, if you go, it looks like it's getting saturated. And therefore, this classic quantum momentum gets, in some sense, localized. So there's a whole host of connection of this. So this phenomenon is called dynamical localization. There's no disorder in the system, but there is some effective kind of disorder. You can do a mapping to Anderson localization problem. But suppose it was the first example of some quantum suppression of classical chaos. Okay, so you have some classical chaos. It seems to make it milder in this. And this was experimentally realized with cold atoms, and there are experiments which continue to this date with many, many variations and very interesting applications since 1995 of this kind of saturation or suppression has been seen for a long time. It's not even, you just take bunch of initial conditions, there's no Langevin, nothing. Langevin involves noise. There is no noise. There's only chaos. Yeah. Yeah, you can. Like KM is a perturbation theory. So, yes, but it depends on how large is your K and so on. For very small K, you can do perturbation theory, it might converge. But by and large, we are interested in non-perturbation. K is 5, for example. It's gone well past perturbation theory applicabilities. Yeah, it will follow. So this time, you see a short time here till it is following classical quantum correspondence. That's a time I'll come to, an Ehrenfest time scale. So that will keep creeping up as this tau h bar tends towards 0. But there is another interesting feature if you look at this expression here. If tau h bar is some integer multiple of 2 pi, in fact integer multiple of 4 pi probably, this entire term will be 1. It will disappear. Tau h bar is some 4 pi. and this whole thing will be 2 pi times integer square. So this whole thing term is 1. It's as if there is no kinetic energy term, there is only this cos cube. So this is a purely quantum effect. You won't have classical limits corresponding to this, and these are called quantum resonances to emphasize the quantum nature of this. So tau h bar is 4 pi is a quantum resonance case, and in this case there is ballistic growth of this momentum. So it goes not only as t, it goes as t square, which is very easy to also analytically obtain because you have only this, only the kick part. If you have only the kick part or only the free part, it's very simple to do. So, but you can see that it's t square, that is even more than the classical. So there is you can go from something which is suppressed to a ballistic growth more than that of the diffusive classical growth, and there's no classical equivalent of these resonance phenomena. And people have done experiments to do with this, as well as fractional multiples of 4 pi, anti-resonances, various kind of experiments have been done with this system. Okay, so I'm now going to go to, yeah. Yeah.
So tau is like related
to the time, yeah. 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 The time between the kicks is controlled. But you see, it's quite fine-tuned, right? I mean, it's quite interesting that, I mean, experimentally you have to fine-tune to some value and keep it there. Yeah.
So these resonances are not the resonances.
No, not the nonlinear resonances at all. In fact, there's no classical equivalent of this. Yeah. Yeah. Yeah, for a given h bar. But you see, in experiments, in atomic units and stuff like h bar is 1. So it's not as if we are doing quantum experiments. So, yeah. You have to scale everything according to that. Okay. Now, we saw all those pictures on the torus. This is on the cylinder. By the way, there is a fair bit of difference between cylinder and torus. Cylinder is basically like a scattering problem because your momentum can go to plus minus infinity. And the spectral nature of these unitary operators are in fact very involved. The spectrum of this infinite dimensional matrix, whether it is discrete, whether there's a continuous part of the spectrum, there is a lot has been known. People have worked on this for some time, but it's actually a complex spectral problem. And there can be Hofstadter butterfly kind of effects. There's a whole host of possibilities. But if we want to study bounded systems, like the kind of quartic oscillators and so on, we would like to keep things in a bounded region, things not scattering away. We would like bound spectrum. So let's try to, and we know that the standard map is something where the momentum also has a periodicity of 1. Therefore, we could, and the classical phase space is a torus. And therefore, we can try to study quantum mechanics on a torus. And so that's what I'll be doing. So torus, unit torus again, we'll take modulo 1, so 0, 1, 0, 1. So now there are periodic boundary conditions both in position and in momentum. Momentum space also, wave functions will be periodic with period 1. So remember our arguments, inner product, this transformation functions, which are just Fouriers. If Q is periodic, it implies that the momentum is multiples of h. But now momentum is also periodic, so the position is also forced to be multiples of h. So both position and momentum are on a finite discrete grid. But Q and P themselves cannot be larger than 1, and therefore this n and m cannot be arbitrary large numbers. they have to lie between 0 and 1, and therefore these integers themselves must lie between 0 and 1 by h. And therefore, if we identify 1 by h to be a number, integer, capital N, then these numbers, these integers m and n lie between 0 and n minus 1, where this n is giving you a scaled h bar quantity, where this n is simply related to h bar by h bar is 1 by 2 pi n, and the classical limit is n going to infinity. So this is basically finite quantum mechanics. Position and momentum eigenstates are finite discrete bases, which are just this discrete Fourier transform. Okay, so in fact, this entire quantum mechanics was developed. Schwinger developed entire quantum mechanics by going to discrete spaces and then making this periodicity infinite. Discrete quantum mechanics is there in a lot of physics. But for us, we just want to use it to understand basic models like the standard map on the torus. Okay, now the position eigenvalues, if you wish, are just these fractions, and these momentum eigenvalues are these fractions. Now I'm going to generalize this a little bit. I'm going to say that, okay, let's take a translation operator in position. Yeah. No, I'll come back to kicked rotor. I want to study the kicked rotor on a torus, so I'm setting up the kinematics on the torus. At this point, I'm not talking dynamics. I'm just saying how to do quantum mechanics on the torus. If one is familiar, we can move on with that. But I'm just introducing that because sometimes this is not a standard part of the thing. Yeah. Good question. Asked like a good experimentalist. So, indeed. Well, again, some kind of a Brillouin zone interpretation is possible, number one. But two is actually there are models where there is a natural, like for example, again, this momentum periodicity is coming from some crystal momentum. For example, in the so-called Harper model, it is cos p plus cos q. So both of them are, this is the, dispersion relation comes from this. Then there is another motivation. I talked about these resonances, quantum resonances in the cylinder. Now, you can take not just 4 pi, but 4 pi times some rational number, and that will actually give you some, you can show that that's equivalent to some torus, equivalent to this torus. In fact, with these kind of boundary conditions acting like a block phase, when you are shifting by a period, you acquire a phase. So this is also, you can also think about this as some special case of the maps on the cylinder. Okay, so there are these things, but actually my motivation is to study things on a bounded phase space as a model. But I would say that experimentally this is not something which, it might need more, thinking to implement than a straightforward thing. Also, it being a finite dimension, it is a lot of, you can make connections to a lot of finite dimensional quantum information that has been done. I should also mention another thing which I'm not going to, I'll just mention but not in detail, is the kick top, which is another model which is extensively studied. There it's also finite dimensional. The finite dimension there comes because of angular momentum conservation. And there will be some total angular momentum that will determine for you the Hilbert space under which you need to act. So there also it's finite quantum mechanics, but instead of the torus, there the phase space is a sphere. Okay, so that is sort of, a lot of experiments have done that case of the kick top rather than of the torus quantum mechanics, as far as I know. I could be wrong. No, there it's angular momentum, so it's discrete. It's discrete and it's finite, but it's not periodic. Huh. On a sphere. So yeah, so the theta phi there refer to the coherent state of so it's on a fixed angular momentum sphere. Angular momentum is, yeah. You mean a torus mathematics or finite mathematics? Yeah, so it depends on your problem. Suppose you're, but actually most of the most of the experimentally realizable things are all finite dimensional because of just energy conservation and other things. Okay, it's finite dimensional. It's not periodic boundary conditions. That's all. Okay, so here also you can deal with physics which is not reaching the boundary. Say, okay, you're not interested in that. That will be the equivalent of the cylinder thing. But yeah, but I want to think about these as models of bound systems. Okay, maybe I will just set this up and then I will continue on Wednesday. It looks like that. But okay, so here is a discrete position Qn, and there's a shift operator which is taking it to the next position. Okay, Qn plus 1. So this is a unitary operator. And if there are totally n states, if you shift it by n, you get Qn plus n. Now this should be equal to the original state Qn, but we don't require that it's exactly the same. It's only same up to a phase, 2 pi I beta. So these are like an Aronoff-Bohm kind of phase. You're going around a circle and you're picking up a phase. So it's actually like a flux line which is threading that circle. And actually it can be used to control time reversal symmetry. So these are important things. And similarly with momentum, you can shift momentum using this translation operator. And momentum can also acquire a phase when you're going around. These phases were set as 0 earlier, but you can now include these two phases. These phases can be used to control other symmetries like parity. And these now form the role of the position and momentum operator. They don't commute, and this is the commutation relation now takes the role of this finite discrete translation operator called the Weyl commutation relation. TP TQ is related to TQ TP by this phase. You can derive the usual commutation relation of QP by letting n go to infinity for large n. And the position momentum transform is almost a discrete Fourier transform, except that it's now generalized to phases alpha and beta. Notice that the translation in position is given by beta, that will appear in the momentum quantum number. And the alpha, which is in the translation and momentum, will appear in the position quantum number. So these are numbers within our control, and the position translation operator, momentum will be an eigenstate of that. And that is, these are the eigenvalues like this. And the other way around, for the momentum translation operator, the position states will be eigenstates. Eigenvalues will be exponential of this. So we identify this to be the position eigenvalues, if you wish, and momentum eigenvalues. But strictly speaking, on a torus or finite Hilbert space, there is no position and momentum operators. There are only generators of position and momentum. There is no infinitesimal generators because there's nothing infinitesimal here. You can go by 1 unit or nothing. Okay, so you should not define Hermitian operators as generators. You can define them as Hamiltonians, but as generators of, it's best to define only unitary operators. Yeah. Yeah, otherwise there will be some uncomfortable minus signs here. So, position and momentum, they are not exactly on equal footing. They have this minus sign also from Hamilton's equations and everything else, and they come from this conjugate relation. So that's the best. Otherwise, if you want a plus sign here, you have to define a translation operator acting on a bra rather than a ket. Just you would want to do something like that. Okay, so now we will define quantum maps like this now in a total phase space. So quantum map in position representation, we will just take the head zero, which is a function of momentum, and we will, instead of putting the momentum, we'll put these discrete values. Okay, and then to find the position representation, we have to do a Fourier transform, which is a discrete Fourier transform. This is already diagonal in the position. So we can have a position representation of this map in general with any general head 0 and V on a total phase space like this. It's a finite dimensional exact unitary operator. There's no need for any truncation and so on. Is efficient to implement numerically because position and momentum are related by a Fourier transform, and Fourier transforms are done efficiently on the computer using the fast Fourier transform. So you can do a fast Fourier transform. This will be diagonal in the momentum. Another Fourier transform to make it again back into the position space. So and then position space is already diagonal. So these two are diagonal, can be implemented efficiently, and a Fourier transform. So for the standard map on the torus, so this is the Hamiltonian again. You see, it's a very simple operator, no Bessel function, etc. If these phases are zero, you can write this. There is a small thing because it's p square and not a periodic function of momentum. You need to restrict n to even integers. Then you have a proper map, and you can write a quantum map on the cylinder to be of this very simple n by n matrix, and that's the form of it. Okay, so we can study these and compare it with the classical. So that's our goal for day after. So let me stop here because then I would, yeah, okay. I'll,
Like p square by 12 plus dq example which you studied today.
Yeah.
You were saying p is like nh, all those things, and p actually I think sometimes you were saying momentum, sometimes
angular momentum.
Is it momentum or angular? That's I got confused.
Yeah, sorry about that. So in the standard map, it's best to think about it as angular momentum. Yes, best to think about it as angular momentum because the angle is the conjugate variable. But I'm using Q and P always, so I'm just calling it momentum loosely, but it's properly angular momentum. Okay, yeah. Yeah, I'm still taking p square. That's why I'm restricting n to be even, so that when you translate this, this will be having a symmetry of capital N. Un plus capital N will be equal to unn prime. Yeah, that is called the Harper map. So that has been studied. Similar features to this. Huh? No, sine won't be anything different from that. But here with cosine p, people have studied this is the Harper map. As a lot of condensed matter people have also studied this from other, the problem of electron in periodic magnetic field and so on. Yeah. Linear NP, yeah. So there are relativistic versions of all of this thing, but not studied intensively, I would say. There are relativistic billiards, for example. There are more recent works on that, as well as probably experiments connected to that. Yeah. Lorentz invariance, you mean? I mean, whether discrete time. Whether your equations, I guess in a particular frame you can, but I don't know what will happen to relativistic invariance in that case. I'm not very sure. You're talking about kick systems. What has been studied most is things like billiards, which don't involve any kicks. They're autonomous systems. Yeah. Yeah, I don't know in this case what would, whether it would make anything, whether it would have any fundamental problem. Not sure. Okay.
So, is there any other question?
Yeah, there are two cases. Both have been done. One is the microwave field, and the other is magnetic fields, large magnetic fields. You're asking where is the manifestation of chaos in that? So because of the Rydberg atoms, these are highly excited. They take the microwave regime. You can actually, so there was, in fact, it looked like there was something which was looking like a violation of a photoelectric effect. There was an intensity dependent ionization which was taking place in this. And then they found that the source of this was because of the chaotic nature of the electron. You consider a weakly bound electron, high energy, that means, which is, got a field which is oscillating in time. So it's almost like this. Instead of a kick, you have a cos omega t. So there are some solvable versions of this, of a 1D hydrogen atom with a field and so on. I can give you references, but experiments were done by Peter Koch. Then there's a lot of work around this in the 80s. Yeah, so it's the electron motion at the end of it. It's the electron, the Rydberg electron trajectories would be chaotic. Similarly, the case with the hydrogen atom in a strong magnetic field, but there actually what one sees is the spectral effects, so the energy levels, and we'll come to that. We'll come to signatures on energy, eigenvalues, and so on.
What will be this equivalence of Peronius operator for this case?
You're asking interesting questions, but as I said, no, the Perron-Frobenius is not directly U for sure. So, but yeah.
Because we also get in our this many body quantum terms description some in matrix kind of things which take our dynamics from one to another state kind of.
Yeah.
So, like here, those are defined by our mod of this, like what you are calling this sorry, not your, your V actually, sitting at like your
Yeah.
like the first part of that.
Yeah.
So we construct that by having kind of Hadamard product of that operators.
Okay. Yeah.
So that's why I'm asking.
I see. Yes.
Related to your some part of it, not the full part of it.
Yeah.
Or maybe I say, like if this Boole resonance, it is possible to calculate quantum systems also.
Yes, yes, certainly. Yes. So there are calculations, in fact, okay, well, let me tell you one thing where people have thought that they have found Ruel resonances using almost this U itself. But if you look at U alone, the spectrum will be on the unit circle. So there are two approaches. One is to make it a bit noisy, so they add a bit of noise, and then there are eigenvalues lying inside, or they make it a little bit open or non-Hermitian. Okay, so both of these things tend to push the eigenvalues inside, and they identify these eigenvalues inside the unit circle as being related to resonances, to the Poincaré resonances, to the Polychord-Rouel resonances. Yeah, so there is that approach. I'm not sure exactly how kosher it is, but that is what people have done so far. There is, first of all, so what is a Perron-Frobenius? Perron-Frobenius will be taking a phase space density to another phase space density. Okay, so here, first of all, there are no phase space densities in the quantum. So, so if you ask for a density, like for example, U, it's acting only on the position space or only on the momentum space. There is no joint, there's no action on both of them together. So if you ask what is the operator which is acting on the equivalent of a density matrix, that is really more well defined for open systems, things like cross operators and all of that. So that's why I think that these things work, of what I said about adding noise or adding dissipation. So we have also done some work where we are coupling one system to another. This can be a weak coupling, and then you're looking at the subsystem evolution. For that, you have an quantum map. Now, this is more directly related to the Poincaré, Polychord-Rouel resonances or mixing on this, rather than dealing just with this unitary operator. So I think they must be related, but this is not something which has been super explored. Subsystem descriptions, because that's already opening up the dynamics. Otherwise, here what happens is, in the classical case also, it's really a unitary operator. You have to go to different function spaces to get these resonances. Okay, you'll have to do some continuity, some analytical continuation and so on. So that is, in finite quantum mechanics especially, I don't see that happening easily. So that's why people have put in these other kinds of things to find. But yeah.
Is there any other question? Okay, then let's thank Professor Arul one
Yeah,
more time.
thank you. See you day after.